Okay, so as you discussed the plan for today's session, we are going to look at uh, the concept related to what we call development before the fact technology. So the main idea here that we need to discuss is how we may come up with design requirements and also identify errors before you implement this. So this is what we are going to discuss today, right? If you look at the history of this, and mainly the person who's behind this, we call Margaret Hamilton. She's American computer scientist and a system engineer. At that time, her task was assigned to develop for the spaceships for Apollo and Skylab. So those are the responsibilities given for her for software development. Now, if you elaborate, like this has happened like way back about like 50 years ago, and at that time, I mean, software development was not in the so all the software methodologies were not developed up to today's one, and at that time there was a need to develop software without any errors. We call it flawless software, and especially this is safety critical system, because if something goes wrong, you are in trouble and you are sending people to the space, right? So the idea of this technology we call development before the fact, in short we say DBTF, is to study the software errors. Right. So having said that, at that time, she came up with a unique approach to detecting the errors before it happening. So that was the idea. So for that, what she came up is how do you visually create the system models? That's one of the things, as we already discussed in our previous course as well. Modeling, especially graphical modeling, is very, very important. So therefore, visually creating system model is one way that you can actually identify the errors, identifying software dependencies. So this is very, very important. So the idea of these visual, system models is to you can create code without any errors. We call bug-free code, and the documentation. And remember, in the early days, we were very strict on the documentation. Document was very important at that time. If you go back, the main software development methodology was the software development lifecycle, where the documentation has a prime importance. So as an outcome of this approach of DBTF, they developed something called 001 toolset, right? And that self-generation. So that's what mainly, the idea of this, right? So the key principles of this is we need to reduce what we call interface errors, right? Interfacing means in this particular case, like, for example, let's say we have several modules, you talk to each other. And then that unit test can actually individually check each of these units. But when units, when you want to work units, when they interact each other, there might be problems, right? So when different components in the software system, when they fail to work together, we call it's a interface errors, right? So in these critical software systems, the major issue was this interface errors. So as I told you earlier, the individual component in the software system, because it's a complex one, and each of these individual, there might be problems. So the idea of this is, how do you address the problem with the components when component fails to work each other? How you are going to handle this? So that was, what was the focus in the development before the fact, the technology, or we call DBTF focus. So by applying, the problems happens within the components of the software systems, we can improve the reliability. So which means that the failure, we can say that there will be no failures, or very little or very minimal failures. So you have a very improved, reliable, software system. And also the safety, because that's also one prime importance, right? So what are the key principles, right? What are the key principles? So the main principles behind this is, make sure that when you design the system, from the design itself, you focus on reducing, errors. We call error prevention. So before even you code, within the design itself, you make it as a characteristics that you don't make any errors. So when you are designing a system, you will focus on error prevention. And then when you are building a system, you use a very systematic approach. So software development is, for that, it will not be a ad hoc. So you have a systematic approach. So use of systematic approach, make sure that you build a reliable and safe software, right? So then that can be benefited in various applications and domain. And also this could be work in various industries. You can improve the productivity as well. So as I told you, like, although this was proposed in, sending, spacecrafts to space, this can also be used in industrial applications, medical domain, where safety critical systems are in place. So I hope now you got the basic key concept, basic key concepts in development before the fact technology. So one thing you need to remember is it's a unique approach that they have, and then focus on reducing interface errors, where the errors happening among the components of the software system. And then the key principles include error prevention and use of systematic approach, which can be used in various domains. Right. Now, one of the things that before we talk about the development before the fact technology, we need to understand what are the problems in the traditional system development. So in this part, we will talk about what are the problems in the traditional development. Since we tend to use the traditional development technologies, what are the issues when it comes to safety critical systems, right? So if you start with the first one, the main one in traditional software development is you focus on the fixing problem, not prevention. Remember, we talked about in the previous one, this particular technology will focus on the error prevention, whereas if you look at the traditional software development, we'll focus on fixing problem. That means, like, especially in the maintenance, we will normally we would like to say, okay, you develop the software system, you implement it, and then you maintain it. And when we say maintain it, what it means, like, you are fixing bugs, mistakes. So that is the problem of traditional software development. Okay. And if you focus on the fixing problem, simply you are wasting your time and resources, right? Quality will be degraded. right? So what are the common problems? One, about the requirements. I think we emphasize on from the very beginning in any software development, software requirement or capturing requirements is very, very important. Because if you are not capture the requirements and you design a system, and a later stage, if you want to change it back, it will be a tedious process because you have to change everything from the beginning, which will affect everything. So therefore, mainly when you focus on problems happening, the common problems in the software development, one is the requirement capturing, right? The mismatch of the capturing requirements. And then uh, integrations, as I told you earlier, one of the problems is integrations. When you say integrations, simply we talk about integration issues across the modules. So that means object modules and even different phases. So these are like, common issues. Next, difficulties adapting to changing needs. So uh, so adaptation is another issue that you normally we will handle um, during the maintenance, and so adapting will not be an easy, right? And then the final point is it's costly and risky software maintenance. Software maintenance will be cost, and if you remember, um, so those are like one of the common issues. So as I discussed, for first one is requirements problems with the when you're gathering requirements, integration issues, and then adapting changes, and then software costly software maintenance, right? um if you go to the last part of this, the challenges in reusing and then the automation is like, when it comes to a reusable code base, um, this reusability will not focus in the very beginning when you are designing. If you are not, focus in the very beginning that how to reuse the cost. So if you do not do this in the development stage, it's too late. So normally what will happen, you make the design and you implement, and later on during the implementation you might think of reusing the components. The importance of reusing components are because then once you tested and use, that will actually reduce a lot of burden in the software maintenance. But the problem with the software reuse is usually this has been done at the later stage of the software development, right? So therefore, one of the things that we will not normally not do is you don't see uh, common patterns. So that's why now nowadays in software development we have software development, we have software patterns, right? Because now our technology or our software development has changed, where we will focus on software development patterns. So there are some behavioral patterns and so on, where like we can people have recognized when you're developing software, there are some common patterns are used. But here we will discuss what has happened, early days, whereas they have not concerned about the common. So because if you identify this in the very beginning, then we can reduce the problems at the later stage, right? The next one is the low incentives for reuse and redundancy, because nobody will actually focus in the very beginning about these properties. So therefore, you have incomplete and inefficient code generation. The code we have not optimized, it will be incomplete and it could be inefficient as well. right? So therefore, most of the time it will be manual, right? So inefficient and manual processes, it will be a challenge for the developer. So I hope now you understood that the problems we might have to face if you are using traditional software development. Uh, so we discussed the key concept of DBTF and the issues with the traditional software development. Sorry. And now we are going to look at why this is a solution. So as I told you earlier, now this is what we call, it uses something called preventive approach. So the focus is before errors happens, we can say prevent errors from happening. So we prevent happening errors, right? So that's what we call it, preventive approach. And then at the same time, it's tried to address all the issues in the traditional software development life cycle. It will be an integrated approach, which means it models the entire system and its life cycle. So you will see that there are some graphical representation, which I will briefly discuss. So it models the entire system and its life cycle, right? And reusability. And it will always stress that reusability. When we say reusable, you develop error-free components. Remember, software will be, you can break it down to small components, where if you make sure that each and every components are error-free and it's reusable, that you can save a lot of time, right? So that's the reason why we take development before the fact is a solution for traditional software, right? Okay, let's focus on more on DBTF technology, and this has what we call the formal foundation. It uses formal systems language for defining system. So it has like mathematical expressions, how you actually develop a system. And as we discuss, it prevents a problem. So it has to model all the application and its life cycle. And then the systems we build from here, we call system-oriented objects, right? Sometimes we call SOO, which means that whatever the system we build is system-oriented, not object-oriented. Remember, we normally talk about the object-oriented, right? This is called system-oriented objects, which is you focus it as a whole system, not as individual object level, right? So which means you focus on integrating all the objects and their functionality, which means you are focusing on use-friendly and a formal way to represent. So now you understood that this is based on the formal system languages, and you focus on the system level, not like individual object level. Now, when you want to build this system, sorry about that. When we look at the advantages, as I told you, like once you identify the reusable components, it maximizes the reliability and the flexibility. And then it also supports performance analysis and design integrity. You can enhance the reuse. When we talk about the reuse, then you can also incorporate automation as well as evolution, right? And the focus is in quality and as well as productivity. So preventive. Now, and curative. Curative is the traditional software development. Usually, we will. What happens is you have continuous testing process to eliminate the errors. But in preventive approach from DBTF is prevent error from happening. And then in curative approaches, usually you can accelerate the development by adding resources, maybe adding more developers or providing more time, right? But whereas in preventive approach, we try to improve the efficiency. And how do you improve the efficiency? You are trying to build a system where you use reuses, using whatever already developed, where error-free components, right? Which eliminate unnecessary processes. So reusing error-free components, basically the focus, which improves the efficiency. And from the very beginning, you have to reuse the components you develop, right? And this will save a lot of time and money. You don't have to develop unnecessary developments are very minimal, since you are focusing on efficiency in the development stage itself, right? So usually we would say every 10 successful users save 10 unnecessary development. So if you can make sure that you can actually use whatever you have already developed, which will saves quite a lot of time. Right. So focusing on this, as we already discussed, I think I discussed this earlier. So it uses a formal theory and focusing on integrity aspects, uses what we call the system-oriented objects, and then it's totally dependent, but that means in DBTF we use some of the terms. Their semantics mean the meanings are dependent, but not the actual real use. Syntax is independent, right? You will see like what I mean by this. So how do you build the system? So if you look at the steps of building a system using the DBTF approach, you use to model this with the language. So I told you guys using a formal language. And then so you use the formal language to analyze the model, and then you make sure that the model is correct, right? So I told you like you want to prevent errors. Then you develop the software implementation and also the documentation. Then you can test and refine the system, and then you can use testing every development step. So, so in brief, you can say defining the model is one step, and then you analyze for correctness. And the output will be this, it generates error-free code and a documentation, right? So if you look at the foundations, these unique concepts actually based on the axioms and universal set of objects. And then this is applicable throughout the entire software development life cycles. And then if you focus on the who are the users of this, there will be managers, engineers, as well as end users. And the ideas will actually coming from the system theory, formal methods, formal linguistics, and object technologies. So actual use case for this is actually from Apollo space mission, as we have already discussed, where they want to reduce the interface errors. Right. If you look back about this particular technology, it started in around like 1968 with the Apollo space mission. And then before that, they have not used, they are sending aircraft without humans or with animals. But now when they want to send, man, the humans were involved in sending them. They want to make sure that there's no errors in their software developments. They usually say that interface errors are accounted for 75 of the errors. So that means in any software development, if you focus on particularly on the errors happening, 75% of the time, they say they are based on interface related. And the what happens during this, they have developed a very systematic approach to eliminate those errors. So that was happening, and that's how they have actually developed this technology. Right, now I will focus on some graphical representation and use of some formal languages. But remember, this is a quite outdated one, although it's useful nowadays as well. But idea is we need to understand how people have made these complex software system in early stages. So during this integrated modeling environment, we are going to focus on two main what we call the graphical representation. We call functional maps and type maps. So I told you, like, they use some graphical representation for the model development. It was a recursive and reusable approach, but the two main maps they have used is F maps and T maps, right? So if I talk about the two types of maps, F maps simply represent or describe the dynamic behavior. That means kind of actions or the transformations, right? So you can also say it captures the function and the time behavior, right? So functions at each node, how tasks flow to their subtask. Idea is that whenever there's a task, then you break this task into subtask, and how this control happens actually represent using the function maps. Mainly function, how a main function decomposed into multiple other sub-functions. Whereas there's a second map we call T maps, or we call type maps. This actually describe the static structures like objects and their properties, right? And then, like in object orientation, that when you have different, objects like parent and the child object, that child usually inherit properties from parents. All these were possible here as well, right? So the T maps actually representing those behaviors. And finally, we will use in these two types of maps, we can ensure functionality and also the structure. They are connected to each other. Remember, the functions are captured in F maps, whereas the structures are captured in T maps. So by using these two, so they confirm that they capture the functionality as well as the structures, and they are connected to each other. So that's the idea that mainly they were referring to. Right. Okay. I think I should give some examples for what these F maps and T maps. So let's look at some examples as well. Right. F maps, T maps, as I told you earlier, F maps functions, and ideally they talk about sub function, which we can call the children functions. T maps, the types, and then how you are control over children types, right? So inheritance is one of the properties which I also discussed. And then F maps control transformations, one state to the other state, right? And the primitive types will be in the bottom of the T maps. Right. Let me give you some graphical representations. I have talking about from the very beginning how this happens. And this is actually simple graphical representation where you will see the two maps. One is F map and then T maps, right? And you can see the two types of node in two maps. You can look at the functions are here. Function breakdown we can graphically represent, and then how these are connected to each other. So that is also there. And then you list some constraint as well, because like any functions, there could be some constraints, right? So in type maps, what you have is types and methods are listed here as well, like is objects, or in object-oriented programming. If I relate this to object orientation representation, this is like your parent and child relationship, right? And this is like your superclass, and these are subclass kind of relations. So that's why you see some relations are here, right? So that's the basic representation. So now let's look at how the design process happens with these two types of maps. And usually they start sketching what we call the type maps, because that's the first step. You identify the structures of these objects, right? So you start with what we call the type maps, and then you use F maps. There you capture the functionality. That when you say the function F maps, they actually based on the T map structure that you have developed. So you start with the T maps and then you develop the F maps. So the type map, it provides, as I discussed, structural criteria. How do you evaluate functional partitioning? In F maps and T maps, then divide the system into functionality, natural components. Because once you realize how the structures and functional divisions are, then you understand the natural division of the components. Remember, I told you the software, a complex software system made out of multiple components. But the problem is, how do you divide the components, right? So when you have the type maps and functional maps, then when you look at both, you will realize, okay, what should be the natural, partitioning of this, right? So then if you follow that, the idea is you are making minimal errors, right? So that means even before you develop, you understand this. Remember, still we discussed the design phase. So in the design phase, if you understand the structure of the system, all the objects and their relations, and then their functionalities, now before you build, you understand, right? So that's basically the use of F maps and T maps in the design phase. Right. Let's look at some primitive structures in this DBTF technology. Primitive structures, usually we talk about the dependent and independent, and then we have decision-making relationships. And usually you have a formal set of rules for each structure. And as I discussed earlier, the idea is we need to eliminate any interface errors. So let's look at some examples. And in this example, I'm focusing on make a table. And the idea is very simple, like how do you make a table, right? And how we can use a functional and functional maps and the type maps in the system design, right? So if you look at how we can do this, the idea of making a table, the requirement is we have to build a system for making a table. So now we have to look at like what are the properties we have. We know if you look at starting from the inputs, uh, you need wood, right, to make the table. So the input will be the wood and then the output will be a table, right? And then we know, so that means how do you map this wood into your table? That's the functional map. You get my point? Functional map is you need to capture like your input is wood, the output is a table, right? So that's make a table. And then type map, the types. The type map on the side, I told you like it's a structure, right? So for example, how do you make a table? Now you can notice that. What is a table? Table, you have a tabletop and you have a legs. Yes. And then if you look at the top, then we know we make use of wood to make the top, and then depend on whether we are going to use a hard top or soft top, right? That you have to decide. One of these two could be used to make the top of the table, and then you will have to have a set of legs, and the legs will be made out of wood. So you can see here, the type map is the one actually I told you will be the first thing to look at the structure. So you see the table is a combination of top of the table and the set of legs. And then top of the table, you can have, hard top or a soft top. And the legs, the set of legs are, you comprises of, individual legs, right? So that's about the type map. And the functional map, if you look at here, the idea is you provide the wood, right? And let's say this is like a kind of a function we have. Function will create a table. So the ideal what we expect is provided that these two inputs, the flat wood and the round wood, right? It will create the table. Output will be a table, right? And then, now you have to understand how you actually provided the wood, how do you get the table, right? The first one is you have to assemble. So that's what you will notice here. There will be something called assemble. Given you have top and the legs, this should actually, assemble them each other in the correct order, right? The next one is you have to create the top and the legs, right? So that's what this function is. Make a parts, provided that you have flat wood and round wood, this will provide a top and the legs, right? So providing that, then you assemble it, right? So the next question is like, how do you make the parts? Now, when you're making a part, you know that you have to make the tabletop separately and the leg separately. So you have two functions to make the top. We use flat wood, and to make the legs, you use the round wood, right? Which will give you the legs and the top. Again, when we make the top, remember we discussed here, the top could be hard or soft, right? So depending on what you want to do, this will be an operation between the two. If you want a soft wood, you will create a top using this function. If you need a hardwood, then you use this function. So you understand this. It's a very simple example that we have discussed here. right? Creating a table and use of T maps and F maps, right? So in similar way, you can do this for even a software as well, right? Any system, first you need to identify what are the inputs and what are the outputs, right? For example, if there are users are involved, you know that you have to take care of their user information, and at whatever the inputs, the data items requirements you can identify, and then you have the outputs. Now, let me give an example. Let's think about online booking system, right? Let's say we want to create an online booking system for flights or hotels or even in the train ticket, whatever it is, right? So if you look at the functionally F maps, what is the input? The input will be your user information, maybe your name, maybe your payment information, and what are the booking dates. Like in a flight, for example, you need a date and you have a destination and you have seat preferences and so on. So those will be the input to online booking system. What are the outputs of the system? The system should output the booking confirmation, like ticket or the reservation code, right? If you make a payment, that the payment is the output. So you understand the input and output now. Okay, sorry about that. Then we have to understand what are the different components that you have. Now, for example, if you look at the component wise, we need to understand that there will be a user interface, there will be a database. If there's a payment, we have a payment gateway, and then maybe you can have notification system, right? And then you have to identify the relationship as well. So now, if you use a DBTF approach, so you have to model how the data is flows from component to other components, right? So what are the components we discuss? I told you, like in the booking system, we can talk about the user interface, database, payment gateway, or any notification system. You have to define how it actually interact each other. So user interfaces, for example, has to pass the input to the database. The database has to interact with the payment gateway, right? And if you think about the payment, and payment is confirmed, and then maybe you have to notify the user and confirmation to the user. So likewise, you can identify. So remember that this everything we do in the design stage. So this very, very important that you identify the different types as well as the functionality, and how do you put them together to reduce this one. And actually what they have suggested is this. So you identify the types, the structures, as a T maps, and then you identify the functions using F maps, where you can understand what functionality we need to develop, right? So if you look at the um, uh, real world applications, this can be used in real-time distributed environments, banking, manufacturing, software development, of course. And then one thing is you can do this in parallel and you can trace, because everything is well documented, represented in a manner that you can trace how you have actually developed a system. So by using this, the advantages you will get is you can reduce the interface errors, you can improve the system definition and organization, and you can facilitate the reusability as well as flexibility. Right. The challenges. Now, understanding, although I explained about the make table is a very simple one, but to apply this to a very complex software system, for example, it's very challenging. Because the first thing is, how do you identify the structures, like their relations? And then once you identify these structures and how do you map it to the functions, might take time, right? And you have to make sure that these models are accurate, because otherwise, when you're going to implement, there might be an issues. Right. So the primitive structures, control structures, if you look at the relations, we can talk about the dependent relationships or independent relationships or decision-making relationships. And then you can use a set of rules for each of these structures. So you can, eliminate any interface errors in the definition phase. And idea, as I discussed, is how to prevent, errors happening. Okay, so if you go back to my example, the very first function that in the top of the function that we have observed in make a table example, we have two inputs. We have flatwood and roundwood. Those are the inputs, and the table is the output. And then we have make a table, and we have two parts, make parts and assemble. I can go back and show you. So in this example, you have noticed this is what we will discuss. We have two inputs, flatwood and the roundwood, and this is the output, right? And then you have some relations, right? For example, we have join, we have include, we have O. This is for controlling dependent, independent decision-making functions. So for example, when we say make a table, we have make parts and assemble. It's a join operation, right? But it has to be done to complete. So if I go back again, you can notice here, we have join here. That means to accomplish or making table this one, when you go down in the functional units, we have two functions and you have to perform these two. Both should be included, right? It's a join operation. That means you have to, complete the making parts. Once you have this, then you implement this one, right? So it's a join operation where you finish the top and the legs, and this can be used to assemble to generate, the table. And it's a join operation then, right? So you make the parts and then you assemble it, right? So then you can also have include. So if you look at the make parts, you have to have two other functionalities, that is top of the table and then also the legs, right? So if you go back to my example, so making a parts, we have to make the top and the legs. So one function will create the top, and then the other one, legs. So both of them are included here to create the top and then the legs. Then you can have operation. In this particular case, you have seen when we create the top, we have to decide whether you need the hard or soft. So depending on the requirement, we are going to select one of the function. So that is what we call the operation. Right. Then how do you decompose the types in type maps? Right. So, so like what we discussed in the functional maps, type maps also we need to identify what we call the parent and child relationships, right? So for example, uh, uh, actually this refers to my figure. In my figure, if you look at it, the table, we have two parts. We have top and the legs, right? So some are dependent, some are independent, some are decision structures, all these, right? And also tabletop, then we have again two parts. We have hard and we have soft in legs. We had individual legs, right? So when you define using these primitive structures, so we were discussing about the properties or the system with these defined structures. So we can have event interrupt driven, and then traceable, recognizable, reconfigurable objects. Provide unique priority. You can notice that what happens in when you define this with the structures, especially in T-maps, we identify, for example, in our example, how do you create a table? So if each is the top of this, then you notice that there are two parts, the top and the legs. So the priority order is already defined, right? And then you can also identify independences and dependences. And then sometimes you can also identify parallel and distributed processing. So parallel means like some functions can execute at the same time in parallel, right? Or some functions can be distributed into different functionality. So because of that, it maximizes the flexibility, right? And you can get advantages of parallelizing, which means you can perform multiple tasks at the same time. Right. What are the defined structures for the designs? The idea is we need to accelerate the process of defining and understand the system, and we have to use non-proprietary structures can be used for asynchronous, synchronous, and interrupt scenarios. As asynchronous means like it will not happen at the same time, synchronous in the same time, and sometimes you have to interrupt. Or these ideas sometimes you might have learned in places like operating system when you have like multiple processes are handled. So the same can be applied here as well. And the patterns we will create using F maps and T maps. Okay, to conclude this, what we have learned with our simple example is how do you define components, structures using primitive structures, and how do you provide the flexibility, how to understand the repeated use, ordering, and selections, and then how do you get primitives and ideas are inherited from the rules of the primitive. So those are the ideas we discuss of this. And then when we talk about asynchronous and synchronous behaviors, again we can define primitive structures, and then you can also use user-defined structures. For example, if you take coordinate task system, we can have dependent, communicating, concurrent, synchronous, asynchronous functions. So that means depend on our requirements. So some of the things will be dependent on each other. Now, for example, when we say join operation in our previous example, so you have to make parts, and then it depends on finishing that, then only you can assemble it, right? When we have user-defined type structure for TMAP models, you can use various other structures. For example, tuple of, a set of, one of, tree of, and these are different types of structure. For example, in our example, if you look at the legs, legs are a set of leg, right? So likewise, we can define them. So once you use in these ideas, these can be, reuse, which is very useful, and we can minimize any errors are happening when you're using reusable functions. Right. The next thing is, now that we have understood in brief how the type structures, that means the structural and also the functionality using F maps and T maps, how do they integrate each other, right? So integration is set for manufacturing company, and then that will be ready for automatic development and production ready code. So once you have defined all the structures and all the functionalities, then it's a matter of development, and you can develop into code, right? So F maps, what happens? It will be primitive operators on the T map types. That means I told you in the beginning, we first identify the structures, and then we identify the functionalities. So in the functions, you will have all the T map types. So let me go back to my example again. Now, for example, here, these are the table. And then you can see we have table, we have top and the legs. And then we have, for the top, we use one of these, wood types, soft and hard. And you can notice that here we will use all these types, remember? So for example, here, if you lose, so these are the what we call the types that we have defined. We said top, right? We said top. When you say top, so you can have top here. So we have top, we have legs, we have leg, and we have hard, we have soft, right? So all these are actually defined, the structure. Now, if you look at the functionality, when we say make a table, and then here you will notice that you are using flat wood and then round wood, and then here we are using these structures. Here we say assemble the top and the legs. Yes. And then make parts. Again, these are inputs. This is input. And this is like the output that we expected from here. So we have top and legs here as the output of this. Here we will have also table. Table is also here. And then we use this to make the top, and then here the legs. And then we have the top, and then here the top. In this particular case, you see we are using a different types of woods are used. So in that manner, we clearly have an understanding about what structures or what types of objects we will have, and how do they functionally manipulated using FMAP here. So everything will be very clearly defined if you use T-maps and F-maps. Right. Last couple of ideas. If you use Universal primitive operations provide some universal primitive operations for controlling objects. You use create, destroy, copy, reference, move, access value, detect, recover errors, and access object type. And it also facilitate manipulation and understanding of different object types. And we will also have type maps and object maps, or map, we call it. So this helps the system to understand better. Right. If you look at the properties of TMAP, TMAP properties ensure proper use of objects in the NF map. So I think I stressed earlier as well. And control spatial relationships between the objects in the TMAP. We clearly understand the table consists of top and the legs. Reference to an object state cannot be modified. There are future reference to that state. So these things need to be explicitly stated in the diagram. And you need to reject values exist in all types for error recovery. So remember, we will focus on error prevention. Right. Using primitive operations, for example, rotate ARM hardware system use primitive operation for numeric calculations, and universal operation replaced with the twice in the example, and function qualifier select unique TMAP parent-child combination. TMAP, expressive power and relations. The type maps enhance the explicitly defined relations. For example, stack of bearings describe use of D sets of structure types, and retain hotel with bill object independently related to cap surface. These are actually some of the example which I will explain or I will share with you. Last slide on this, as we discussed the use of this technology, especially the graphical representations I explained to understand how system can be decomposed, especially with the structures as well as using functions. So reuse is the power of this particular technology, and using that we can identify and what are the places that we can reuse and integrate. So ideally, once you properly design these, that could be define and use each other as reusable. So that's the model. So for example, earlier I explained about various different components for online booking systems. And for example, the component I explained were things like user interfaces, databases, payment gateways, and also notification systems. Those, once you define it, those could be reusable for any software system. So that's where this is very, very useful. So once you have identified the functionalities, the structures, then when you develop another system, you can easily use same functionality when you're developing software, right? So these are the theory that I want to discuss, and the most important part that I actually covered is FMAP and TMAP. And if you have understood how the simple problem that we have tackled here is breakdown in the structure wise as well as function wise, that's what I want you to understand. And then explanation of why this particular technology is developed in those days, which is for safe critical system. So if you have understood that part, I think that's the main purpose of this session. Right. With that said, we'll finish the theory part. Then I have a small, work to do. So in this particular work, I will have two questions, but I will give you right now one question, which is more on theoretical side. And I want you to answer within half an hour, and then you can submit the answer as assignment. It's an individual one, so each and everyone can have your own version. About half a page to 1 page is enough, but not more than that. Limit your answers to in half a page to 1 page limit. Before we finish,